So next talk is called Finite Elements and Higher Performance Computing, and the speech will be given by Marc Serra and Jesús Bonilla Toro.
So, good morning. Shouldn't be 9. Good morning, everybody. He's Marc. I'm Jesús Bonilla, and you like or not, equations govern our lives. So, from heat flow to fluid flow, passing by elasticity, everything can be modeled with an equation. The problem is if we know how to solve the equation. For example, by hand, we can only solve really simple equations such as the heat flow in a rod or the elasticity in a simple supported beam, or for example, the fluid flow in a channel. But if we put in the middle a cylinder, we cannot solve it by hand. So what engineers do in order to solve more complex systems, what we do is model the geometry in a computer, then divide the geometry in very small elements, in very small parts, and then apply some numerical methods and analyze the results. But this is not, let's say, mainly our research topic, because this is happening right now in almost any engineering company. But can we go farther? I mean, can we simulate the atomization of this water jet? Yes, of course, we can do it. And this is our, well, not this in simulating atomization, but in how to go farther and how to simulate much more complex systems. But you should know that this is not for free. In order to perform this kind of simulations, we need to use supercomputers, such as this one. It's called Titan. It's the second most powerful supercomputer, and it's about 1 million more powerful than an average laptop. So the problem is how this is not straightforward to use it. The program running in your laptop is not the same program running in these computers. So we are working on how to go from the program in your laptop to the program in the supercomputer. But let's start from the beginning. Let's start explaining a little bit the numerical methods we use in order to solve the equation. Let's say that the main goal of the numerical method is going from the PD, the partial differential equation, to an algebraic linear system of equations. In order to do that, imagine the heat flow equation and in a rod. We divide the rod in several pieces. We assume that the solution has some shape, for example, a straight line or a parabola or any polynomial you want. And then using some tough math, we are able to obtain a linear system of equations that we can solve in a computer or in a supercomputer. And for example, to show a toy problem, let's say, a small example, imagine the same equation, the heat flow in a rod, that it's so simple that we can do it by hand, and this is the analytical solution. And we have performed several tests, including more nodes. It means making smaller and smaller parts. So this is the first approach in blue, the numerical solution that it captures. It's just a crude approximation. It just captures the general behavior. But if we add more elements, the solution improves. But notice also that the time needed to solve the system of equation, it's also greater. So it's improved. With 50 nodes, it's more or less we captured the correct solution. But the CPU time has also increased a lot. But imagine this is for a really simple equation. Imagine what happened in 3D for a tensorial problem, much more difficult, that the computing time explodes. So we need to parallelize. We need to use supercomputers, and Marc is going to explain how to do that.
So the main problems we face when you try to solve larger and larger systems are, first of all, the more information we have in the system, the more memory consumption we will have on the computer, and the memory in computers is not unlimited. So at some point it will break because it does not fit the computer. And the other part that increases with the size of the problem is the time consumption, as we have seen by Jesús. When we put more and more elements, the time of the computation increases. In an ideal scenario, the second graph, We want the problem to be larger and larger and larger, and the time remain constant. And the two first figures is just to show the first. It contains really low levels of information. It can be computed by every computer. But the second is a whole mesh of a complex domain, maybe 1,000 or million of elements. This cannot be computed in a single computer. So our way to treat this and make high-performance computing is to split the problem and take parallelism of the problem. This is a dummy example we have thought about to try to explain what is parallelism. Imagine we want to perform some task, and the first thing we do is to divide it into several tasks. So each one will carry out the things completely in parallel. What may happen is that if everyone does completely in parallel its task, we may not get the right solution. What we want is to go to the right solution, and it's not enough with dividing and recovering the solution. In the middle, something has to happen, some organized, some communication, one saying to each other, okay, I'm done, I can give my ingredient to you. And this is what we try to do with our system of equations. How do we do that with equations? We actually split the domain. The equation is solved in a domain. Imagine this is, for instance, a square of surface of water, and we want to model something inside this domain. And we put a mesh on the domain, as we have seen before. Our model works with a mesh. And for each node, each white circle, we will get an approximate solution of the real solution we are looking for. And we divide our domain into several parts, as we have done before with the tasks for cooking an omelette. So we have 4 different parts. We send each part to one, let's say, one different computer. So each computer will calculate each part here in different colors. And this would be like the abstract scheme of the omelette, but with computer domains, subdomains, and processors. We have 4 different subdomains, and each computer will calculate the solution for each subdomain. The key point of these schemes is that we want to maximize the local tasks performed completely in parallel, but at some point, it's essential to have some neighbor communications. Here, the communications will be performed only on the red nodes, on the interface of the subdomains, that say the shared faces among subdomains. We go on, we have some more local tasks, and at the end, we will recover the right solution for the whole problem. Let's say it in a dummy example. These equations model the concentration of some pollutant, for instance, into water. We have our domain, it's a square. We impose the concentration to be 0 along the boundary of the domain, and we solve it in parallel. So we have one solution for each subdomain. We gather the solutions, first with the mesh, then without the mesh. And as we have imposed, we have 0 concentration along the boundary, and the highest concentration is reached just on the center of the boundary. This is just to check that we are recovering the right solution for the subdivided problem. This is just a surface 3D of the same problem. And this was a dummy example, but what happens if we want to go farther and model this entire car, not 4 subdomains, 1,000 of subdomains, 1,000 of nodes? We need a supercomputer to do that, and this is high-performance computing, how to use these resources to solve this. These are the current supercomputers we use in our group. The first one is Mare Nostrum, located in Barcelona. And the second one is Jukwin supercomputer, located in Germany. It's the most powerful supercomputer in Europe. And just the final words, our group develops this code called FEMPAR. It's able to deal with these different problems. And the greatest achievement is the one that you can see on this. Thank you.